studying thermodynamics? Probably because you have to, but it's a more important reason than that. Thermodynamics is a study of energy and energy transformations. And so when we look at energy transformations, what does that mean? So if I think about energy transformations, what about a fire burning? Think about a campfire. What is going on? You have a change of the chemical energy of the wood into flames, combustion process. Then that creates temperature. You have radiation of temperature to keep you warm. That's one type of energy transformation. So we're looking at different energy forms: chemical, thermal, and we're looking at their transformation between the two. Turn on a flashlight. What's going on there? We have chemical energy being turned into electrical energy, and that current flows through a filament, and the filament creates light. We have energy transformations there. Think about windmills. So if I think about windmills, what do we have? We have the wind's energy is causing the windmill to rotate. And that rotating windmill is connected to a generator in some cases, to a water pump if it's on a farm and you want to pump water. And so we have the conversion of the kinetic energy of the wind into mechanical energy. Now, something that you're all familiar with, or I believe you're all familiar with, is a hairdryer. So how does that work? You turn on a button and you have warm air come out. That's how it works. No. What happens is you turn it on. There's a fan inside, so I have a conversion of electrical energy into mechanical energy, making the fan rotate. We also have current flowing through a resistance, which increases, so I have electrical work being converted into thermal energy in terms of the temperature rising. And, of course, looking at a car or truck engine, so if I look at a car or truck engine, then we have the conversion of the gasoline, the chemical energy of the gasoline, into heat and pressure. The temperature goes up, the pressure goes up, the pistons move, things rotate, everything's going on. So we have a lot of energy conversion processes there. So there are different types of energy forms. So when we think of thermodynamics, there are different types of energy forms. And they change from one to another. And what we're going to do in this course is examine these and examine how this transformation occurs. One of the wonderful things about thermodynamics is that there are only two laws that we have to pay attention to. One is the conservation of energy. So we're looking at the conservation of energy, and that means energy is conserved. So that isn't very much. We have to define what energy is. We'll define the various types of energy, but it's conserved. We're not looking at nuclear reactions where we have the change of mass into energy. So, but for 99.99% of the time, we're just fine dealing with this. In the second law, so this is the first law. In the second law, talks about energy quality. So by energy quality, energy has different types of value. So I can have energy that's more valuable to me, such as if I want to stay warm, heat at 30 or 40 degrees Celsius is more valuable than heat at 10 degrees Celsius. And so we have that. It also gives a direction to energy flow. So direction to energy flow. So in this case, the direction to energy flow would be heat flowing from a high temperature to a low temperature, a fluid flowing from a high pressure to a low pressure. So we could have heat flow, T high to T low. We could have fluid flow from P high to P low. And so that's what the second law does. And we also have a law which is not a law of thermodynamics. We use conservation of mass, but that is a different situation. But we just have these two laws. That's what we look at. And the first law we'll talk about later in chapter 3, and we spend time there. And chapter 9 probably summarizes all the direction of the second law. And so we'll be looking at that. But now we need to think about how do we communicate thermodynamically? So now we need to be able to talk thermodynamically so we can understand each other in terms of what's happening. So we want to communicate thermodynamically. And so, in general, there are two ways that we do this. One is, it's called macroscopic versus microscopic. Macroscopic is on the scale that we live. Microscopic is at the atomic level, looking at molecules. In this course, we're looking at macroscopic thermodynamics. So this is at the molecular level. So we're looking at the interaction of atoms and molecules here. This is at the level of human perception. So the level of human perception is I could measure distance in meters or millimeters, I can measure time in seconds, I can measure mass in grams or kilograms. So that's what we're looking at here. So I'd be measuring T in seconds, mass in kilograms, and that's the macroscopic level. Now so I have this energy transformation going on, I have these energy, something has to be performing the energy transformation, and a substance is what's doing it. So a substance is what's undergoing the energy transformation. So we have a substance undergoes energy transformation. And with the substance, we'll either have a pure substance or a mixture. We'll study about these later. A pure substance or a mixture. So with a pure substance, it's like water. So water is H2O, so if it's frozen, it's H2O. If it's liquid, it's H2O. If it's steam or vapor, it's H2O. It's a constant chemical composition. A mixture is not that way. So it will change form. So if I have seawater and I boil it, the vapor that leaves is fresh water. And so the seawater gets more briny. So now the next thing that we want to look at is systems. So the substance is in something. It's either a constant mass system or it's a constant space system. So we have two types of systems that we look at. So we have a substance, and then we're going to have two types of systems. So let's look at the system. So we have systems. And it's mass or space of fixed identity. And I'll be asking you more about this, so the concept of a system is very important for us to do. So when we're looking at systems and we had the mass or space of fixed identity, it doesn't change with time. So it does not change with time. Oops. So the first of these systems, let's look at a fixed mass system, which we will call a closed system. So a fixed mass system, and we will call this a closed system, and I'll explain why shortly. So if I look at this closed system, and what we're going to do is introduce some other concepts. So I have a system, so I have something like this, and this is my system. Here's my system of fixed mass, and I have a boundary that separates it from everything else, and everything else is called the surroundings. And then everything else is called the surroundings. So if I take this eraser, one of my favorite visual props, and also one that's in a classroom is an eraser. So this is constant mass. So if I have this, it's constant mass. I can imagine about an imaginary boundary around this, and then this is the mass of fixed identity. I can do things to it. I can whack it against the board. I could throw it. I could heat it up. I could do a whole variety of things. And this is my system, mass of fixed identity, a closed system. And closed has to do with the fact that it doesn't allow mass in or out. The mass stays constant. So it's closed to mass flow. So now what I want to do is look at another case. So we had fixed mass. Now let's look at fixed space. So if I look at a fixed space system, and this is called an open system, and the reason it's called open is it's open to mass flow. So mass can go in, mass can go out. So it's open to mass flow. The closed system is fixed mass, no mass can flow. So the open and fixed space and fixed mass system are called open and closed for that reason. And we're going to do that. Now, imagine you went this morning, you're in the bathroom and you turned on a faucet. So you turned on a faucet. So I'm going to draw the faucet like this. So here's the faucet, and I have water going in and out. I turn it on, and this is my fixed space system. So I could draw a boundary around the faucet. So here we have a faucet, and here's the boundary. So the faucet is fixed in space. It doesn't change in time. Water flows through it. And so now what we have another name for this that we sometimes call this volume, this fixed space volume, a control volume. So sometimes we also call this a control volume. So often we use control volume if we're doing some more theoretical development, something like that. And so now I have my system. So I have the substance, such as water, that flows through the faucet. I have a substance, such as the eraser, which is my fixed mass system. And now what I want to be able to do is describe how that substance exists. So we need a way to describe how the substance exists. And we do this, and there's something called properties, and you're going to say a property like temperature, pressure, volume, and mass. You say, thank you very much, I know that. But these are the properties. So these are properties that enable us to describe the substance and what its state is. So we're going to have the state of a substance. The state of a substance describes how it exists. So the state described how it exists, and we have properties. That state is determined by properties. So we have these properties like temperature, pressure, volume, and mass, and other properties, and they describe how this exists. So properties describe the state. And we could say here, e.g., temperature, volume, pressure, mass. So these are properties that you know about, and that describes how they exist. Now we have a precise definition of a property, and it matters, and I'll write it down. So it has mathematical meaning, and it enables us to be able to model how properties are described. Or how properties are represented, I think is probably a better word. So a property is a characteristic quality of the entire system and depends not on how the system changes state, but only on the final system state. You don't have to memorize this, but I want you to be able to understand it. So this is what it is saying, why are you telling me this? And so part of why I want to tell you is that we want to be able to have a mathematical model for our thermodynamic systems. And part of that is we have to be able to describe properties. And so what this is telling me mathematically is the following. So you know from calculus that if I have the integral of dx going from state 1 to state 2, that's equal to x2 minus x1. It did not depend on how the system got there. It did not depend on how the system got there. So properties are differentials. So mathematically, I can represent properties like temperature and pressure as differentials, and they don't depend on how they got there. So for instance, in the room, if the room went from 20 degrees Celsius, let's say 70 degrees Fahrenheit, and it finally was at 90 degrees Fahrenheit. But first, it went up to 100 degrees, then it cooled down to 80, and then finally it got to 90. When I integrate dx, it doesn't care about the path. It only cares about the initial state and the final state. Nothing else matters. And so that's what happens with properties. There are energy forms that do depend on how you change, and that's why we're making this distinction here. We also said they must describe the entire system. They must describe the entire system. Now, what does that mean? Let's take water in a pool. So with the water in the pool, let's draw a pool. So here's a pool, here's the water, and if I want to look at this, I could measure the temperature. So if I have a thermometer, so I have a thermometer. So I could take the thermometer and I could take it and I could have it up here, I could have it down here, I could put it all over the place, and it is possible for the temperature of the water to be constant, in which case we can describe the water as having a temperature of 80 degrees Fahrenheit. And so then temperature would describe the system, and I could say the system, all of the water has 70 degrees. If some of the water up here is 80 degrees and some is 60 down here and different, then I can't use temperature and say that the system is at that. So when T is equal to C, things are in thermal equilibrium. So thermal equilibrium relates to the temperature being constant throughout the system. But now let's think about pressure. So if I think about pressure, and you know that if you're up here on the top of the pool, so I'm up here in the top of the pool, the pressure is less than if I go down and I'm on the bottom of the pool. So you know instinctively and from your experience that the pressure here is greater than the pressure here. So pressure cannot be a property of the system because it varies throughout the system. Not a property. And the equilibrium associated with pressure is called mechanical equilibrium. Even though there's nothing mechanical about what's going on, but that's what it's called, so we're stuck with it. So it's not in mechanical equilibrium because the pressure is not there. So there is an so we had temperature as a thermal equilibrium, pressure has a mechanical equilibrium. So there's an equilibrium associated with each intensive property, and let's talk about that. With each intensive property, you're going to say, what is an intensive property? So I know that's happening. So an intensive property does not depend on how big the system is. So the temperature, for instance, is an intensive property. It doesn't matter how big the amount of water is I'm measuring. It doesn't matter if I'm measuring water in a cup or in a pool or whatever. It's size independent. So intensive size independent. And then we have an extensive property, such as volume. And this is size dependent. And so we have intensive and extensive properties, and they correlate. Like temperature is the intensive property associated with heat, which we'll find out about in chapter 8, I believe. And pressure is the intensive property associated with volume that we'll be finding out about shortly.